Okay, welcome back everyone. Today is Wednesday and today is a quiz day. I set the timer, so I hope timer rings. At 10:35, I give you 20 minutes to do today's quiz. I don't think you need 20 minutes because the quiz is over 3A. 3A is, what is it? Free body diagram for a system of some kind, could be 2D or 3D. You're going to resolve support reactions. That's what the 3A. 3B quiz is tomorrow, which is a truss. Okay, truss could be challenging if you do take a wrong route. Starting from, okay, well, I'm gonna start doing this problem without thinking. Okay, let's just go ahead, find out support reactions, draw free body diagram of this total structure, and then realize, wait a minute, you have pin and pin, four unknowns. How can I solve this support reaction? Oh, it's impossible. Then, okay, those two. No, this is three unknowns. I mean, you can never solve a truss problem just like that within 20 minutes, guaranteed. So every truss problem need to develop starting from a strategy of how can I approach, knowing that if it's meso joint, you only have two equations available for each joint. That means you can only have maximum two unknowns. Okay, so if the entire truss is supported by two pins, that's it. You can never find the support reactions. Those are all four unknowns. You can never solve it because you can only have up to three equations. You need to be aware of those things before you actually start drawing everything and you realize this whole thing is mistaken, erase everything. Then that's it. You can never solve it in time. Now, out of my own experience, when I was young, just like you, truss problem was a nightmare because I spent literally a few hours for each problem, not knowing where to begin with. I draw very beautiful diagram, ended up erasing everything. Please don't do that. Okay. So you need to have a strategy before you actually start drawing something. That's the truss problem. Okay. That's tomorrow. And we're going 3C right now. So 3C homework is going to happen fairly soon. And then 3C, quite important thing is you're going to understand introducing virtual cut and then expose the internal loading up to three things: normal force, shear force, moment at each given cut section. And then especially for the case of the beam is a structure supporting perpendicular loading and moments. You want to know how the internal shear and moment distributes within that beam shear and moment diagram. Okay, so we are going to take a look at those things. So this is the handout. Let's just take a look. Okay, shear and moment diagram handout. This handout actually came from ES202, solid mechanics. This is the class you're supposed to be taking right after this class. This class is ES201 statics. This handout is taken out of ES202 because occasionally I teach this class. Nowadays, not quite often, but I used to be teaching this class when I was a graduate student doing PhD. Every semester I taught this class. I didn't know why, because I thought I was an aerodynamics person. I have nothing to do with this. But anyways, when I was doing PhD, I taught solid mechanics about 4.5 years. There's interesting behind-the-scenes stories, but I'm going to share you sometime. Okay. Anyways, so this is the handout taken from solid mechanics. Okay. So guaranteed you're going to see this again when you take solid mechanics, and then when you see this again in solid mechanics, professors assume that you know this. You mastered this already from statics, so I don't have to cover it again. This is the starting point of solid mechanics. Okay. So this is a proper understanding. You have to master the meaning of each equation. Simple, isn't it? Okay. So this is the governing equation, 4 of them. Actually, 2 of them, and then if you integrate those 2, you come up with the integrate equation. If you integrate the differential equation, what do you mean by that usually? You are given differential equation to relate two things. This is a relationship between shear and external distributed loading. This B is internal shear developed inside of the beam. This is externally applied distributed loading. This is the relationship. If the relationship is given, then you try to integrate to have delta B now. What do you mean by that? Integration typically means you're going to find the area under the curve, right? Do you remember those? This is area under the curve. So we are going to look at those details. So please don't miss those concepts. If you don't understand concept, try to memorize it. It's impossible. It's impossible to draw shear moment diagram. And shear moment diagram is a starting point of solid mechanics. Okay? So those two equations basically relate internal developed shear to the externally applied loading. So if you apply distributed loading over the beam, it is going to affect on the internal development of the shear. That's one thing. What do you mean? dB dx, this literally means that the slope of a shear diagram. In other words, how much shear changes the slope of it, that's what the dB dx, that's the differentiation of certain property. dB dx means, well, what's the slope of this changing function? Shear force internally developed is a function of x. So this is going to keep changing based on the externally applied loading. So what is the slope of that? That's the meaning, okay? So every equation you see from now on, you are going to think about physical meaning behind it. Okay, that's the requirement of engineering. Mathematical equation usually, no, it's not usually, always, it is always associated with physical meaning. Okay, next one, this is a relationship between internally developed moment is equal to essentially the externally applied shear force. This is external shear force. Okay, so this is the beam supported like this. If you apply external shear, what happens to the internal moment? Moment changes. No? Yeah, the slope of the moment changes because of it. That's what the equation says. Okay? Then A and B can be integrated to find out. So having said this is the slope of the internal shear and slope of the internal moment, this is the function of x. In other words, every position, internal shear moment changes. That change could be linear or non-linear, but you can integrate to find out actual change. So how much change of shear happens? Well, if you want to know how much external distributed loading is applied over this range, find out the area of it. Area is going to give you the resultant. That is how much change of shear happens. Obviously, that's what the equation says. Okay? This one too. How much actual moment change happens? Well, that means how much change of shear, internal shear you have. And then over this range, the shear force changed linearly. That means moment changed this much. Okay? So having said that, let's just go through example problems one by one, and then try to kind of each time when we try to solve the example problem, or in your side homework, let's try to go back to those governing equation and try to confirm yourself. Hey, this is what it means. Hey, this diagram is yes, indeed, governed by this equation. Please do that. You can never memorize this kind of thing. You can only understand it. If you don't understand, you don't know it. That's engineering. Okay? So just to try to, okay, I have no clue what Dr. H is saying. Well, just memorize it because I want to pass the exam. That's not engineering at all. It's not gonna give you any success. Okay? All right. So this is sign convention. I think Abby, you basically asked a very good question on yesterday's online session. I really appreciate that. That actually brought up the sign convention discussion. So a sign convention, 1, 2, 3, right? So let's just take a look at the notes yesterday. So this is the sign convention. Okay, wait a minute. Yeah, so this is a sign convention. So if you cut and expose right-hand side of a free body diagram, this is a positive direction of shear. This is a positive direction of moment. And Of course, normal reaction force, we ignore it because it's usually 0 for beam. Okay, so if you cut and then expose left-hand side, this is the positive direction shear. This is the positive direction moment. Okay. And then if it's externally applied shear, this is externally applied shear, such as support reactions at the very end of the beam. This is externally applied shear. This is the positive direction on your left-hand side. This is the positive direction on your right-hand side. If it's externally applied moment, just about any location, this is positive direction, this is positive direction. Okay. So sign convention is important. We are going to strictly follow the sign convention. Otherwise, people draw moment shear diagram and people use, hey, I decided this is positive, and then it's completely flip-flop. We want to have some standard. That's what the sign convention is. So we are going to carefully draw, follow through this sign convention. Okay. And also, this is an important other definition. Suppose if you apply point force, it is going to create a jump in shear diagram with the amount you apply. So internal shear of the beam, suppose this is a beam, you apply point force right here. If you draw a shear diagram, it is going to be this jump because you apply this much shear force. If you apply moment, in the moment diagram, jump this much moment. That's what it is. So those are the other definition. Externally applied point force causes jump in the shear diagram. Externally applied point moment causes also jump in the moment diagram. Let's be careful about that. It's kind of simple. You can kind of notice by drawing shear diagram. And then diagrams must start from 0 and end at 0. This is quite important. Oftentimes people forget about it. Since you're talking about equilibrium beam, it must start all 0 and end at 0, both shear and moment. So at the support point, at the end of the beam, no shear, no moment developed internally. Okay? All right. So next page is quite important. This is summary of shear and moment diagram. So usually we are going to construct shear diagram first. And then based off of the shear diagram, you can develop moment diagram. So let's just take a quick look at what each actually means. So this is the beam. Looks like free body diagram. This B1 is at the end of the beam. This is typically support reaction. So this is considered externally applied shear force, support reaction, B1. So because of this B1, you have a jump right here. Okay? And then there's no distributed loading within, so this B1 is constant. So from here to the point force here, point force P is applied here. So from here to here, internal shear is constant, which is B1. Okay? Then after you apply the force P in this direction, you have a jump in shear diagram. So now internal shear becomes B2, which is less than B1 from location here to here. That's internal shear is all B2. Then at the very end here, you have, probably this is support reaction. Support reaction bring it down to 0. Making sense here? So this is jump up, constant, jump down, constant, jump down. Go ahead.
This is the diagram of the internal shear developed.
Internal shear.
If you would compute at every point, that would be the...
That's right. Suppose if you introduce a virtual cut, let's say, okay, you have a very good point. Suppose if you introduce virtual cut here, and then find out, okay, so what is the internal shear? That's B1, isn't it?
Yeah.
B1. Suppose if you cut here, what is the virtual cut? What is shear? It's B1, isn't it? So from here to here in this range, internal shear is B1. Okay, so that's the shear diagram. So you can understand what is the internal development of shear force of this beam. You can determine those things. This is the diagram. Okay. So okay. And then based off of the shear diagram, obviously you construct the shear diagram first. This is going to affect our moment diagram. Okay. So let's say at the end point here, you have, this is probably support reaction, some kind of externally applied moment, M1 shows up. So this is going to be a jump up. And then starting from here to here, you know the shear is constant. Okay? So remember, the slope of the moment is a function of x, is equal to essentially shear. That means the slope, this is the slope of this moment diagram is constant, which is a linear function, straight line. The value is B1, that's the slope. Okay, because internal shear is B1 constant. That means the slope from here to here, the location where P is applied, slope is constant, linear function. So you are probably interested in, okay, so what's this? So the moment changed from M1 to right here. How much change of moment do you have? What do you think? That's the area of this. Remember? Let's take a look at the previous page. Delta M. The change in the moment is the area under the shear diagram, right? That's what the integration really means. So this is the delta M starting from M1 right here. And then this is linearly increasing because the slope is B1 constant, linearly increasing. So you want to know the value right here. What's the value of moment here? This is delta M. That is area under this curve. So this much area, B1 times this much distance gives you delta M. That's what the equation says. Okay? And then here, since you're applying force P, you have a jump. So the internal shear all of a sudden changes to B2, which is decreasing slope. Slope is decreased here. And then value becomes M2 at the end. And then you have, because of the M2 support reaction, you go back to 0. And then this is also another delta M, right? So how much change of moment from this value to that value? What's that? What's this delta M? Anybody? What's this delta M? That's the area here. Right? Make sense? That's how you can understand how to construct the shear and moment diagrams. You have to always go back to what the governing equation really says. Okay, this requires practice. It's not simple stuff, but you know, you have to kind of understand the concept, the meaning of equation, what the equation really tells you. That's what the equation is really all about. The equation is not simply just something written. No, it's not. It's just basically tells you what the physical change and physical meaning of the behavior of about this diagram really about. And also, this is point moment. Of course, application point moment does not change the shear at all. So in this kind of configuration beam, shear is uniform throughout. Starting from 0, you have a jump up this much, and then uniform. In other words, shear doesn't change at the very end. You have a jump down to 0. So internal shear of this beam is constant. Okay. However, since you apply the point moment right here, you have a change of moment. So starting here, you know, you have a jump up M1. Then here is B is constant, so it's a constant slope. So you can easily find out this delta M. This delta M is essentially this area, right? And then here, you all of a sudden jump down this much. And then from that point on, shear is constant, so you still have the same slope. Then you come up with the value of M2, you have jumped down to 0. Make sense? So the slope of this and slope of that is constant because shear is uniform. But you have a discontinuous jump of moment because of the presence of external moment application. Okay? Go ahead.
If you was to the other direction, you was going up.
In which direction? This
M0.
If M0 is opposite, you have a jump up and then go this way. So M2 is going to be really huge body. This kind of thing. Yeah. Okay. Maybe erase all of those. So I hope you understand the concept of how to construct shear moment diagram. This is quite important. Okay. Once you kind of understand the thing, you can just apply the same thing to just about any configuration you can have. So this is the presence of distributed loading. What does that do? Distributed loading, be careful about the negative sign now. So this is the distributed loading typically applied in negative y direction because that's what the beam does. Beam is going to support this kind of loading. Okay? So negative sign shows up. But so magnitude of this uniform distributed loading is going to be a slope of the shear diagram. What is that? That's what this equation says. Okay? So the slope of the shear diagram, dB dx, b is a function of x. This is equal to negative of distributed loading. If the negative of distributed loading, this w is constant, that means the slope is constant. That's what you're seeing here. This is a constant slope, starting with b1 jumping up here. From here all the way to right here, you have a constant slope of negative is important, negative w0. Negative because w0 is going down to the negative y direction. That's what usually is. So that's why this original governing equation have a negative sign in. There's a negative sign. Okay? Quite important. Okay. So the handout basically says negative sign something. Where? There is a negative sign. Be careful. Distributed loading is usually applied in negative y direction. Okay. Go ahead. Yeah, question.
I understand like the equations, but I have a question about like what the equations represent mechanically.
Oh, that's the meaning of understanding equations.
Shear is it's constant when the forces are in opposite direction, right? Shear
could be up or down, either way. In other words, force developed internally inside of the beam, either this way or that way. This is a normal force. That is zero.
It's just from opposing forces, though, in the material. Right?
It may not necessarily be opposing force. It's because of the external loading, the material need to resist somehow, either this way or this way, internally within the beam. That's what the internal shear loading is. Yeah. So it could be this way or it could be that way. Either way. Okay. So typically, however, the direction is this way, because that's the external distributed loading is usually applied. If this is a beam, you're not going to push up usually. You usually push down. And as a result, the beam's material at this point need to develop internal force like this to resist it. So yeah, that's probably one way to look at it. Okay. And then, of course, equation actually explains it. All right. Good. So once you develop this is the shear diagram. Moment diagram can also be developed by it. So in other words, this is a moment starting with the slope of B1. Slope is larger slope. You understand? Slope is higher slope right here at the beginning because you have a shear is high value. However, this shear continuously decreasing, becoming B2. So at here, slope now becomes lower value of slope. In other words, starting slope is this B1, but at the end, slope becomes B2. Okay? Because slope is a magnitude of shear at each location. So slope constantly changing. So this is a decreasing slope. This is nonlinear equation. It's not easy to figure out nonlinear thing. This is typically nonlinear behavior of moment. But you can at least determine the slope at the beginning here and the slope at the end here. And also, how much change did it happen? In other words, if you're interested in, okay, so what is the delta M here? What is that? Well, moment changed from M1 to M2. How much delta M? Of course, that's the area here. This area is this delta M. You can find out that kind of stuff, okay? So that is the presence of uniform distributed loading. Next, it's getting more and more complicated. Suppose you have nonlinear distributed loading. Have you ever seen this kind of problem? Yes, I can easily create this kind of program easily. Let me repeat, easily, from from instructor's perspective, I can create this kind of problem just as easily. If I feel bad trying to kind of beat up students, I can easily create this kind of problem. I mean, anyways, I shouldn't say that, but obviously this one really indicates that starting with W1, which is the smaller value of distributed loading, but this is going to keep increasing, right? That means, what do you mean? Slope is no longer uniform. Slope at the starting point is a lower slope, right? Yeah. But this slope is going to increase and increase, and then steeper and steeper, right? So at the beginning, you have a B1. This B1 is going to non-linearly decrease, becoming B2. The only thing you can know is at the very beginning, how much slope do you have to begin with? At the very end, how much slope do you have? The slope is W1. W1 is smaller value, smaller slope. This is steeper slope because W2 is bigger. So slope of the shear diagram is a magnitude negative of distributed loading at that point. How do I know? Because that's what the equation says. Look at that. The slope of the shear diagram at a point is negative of the magnitude of the distributed loading. Based off of that argument, you can say slope here at the beginning is W1 negative. Slope here is W2 negative. Of course, W2 negative is larger value. It's a steeper slope. Okay. So what is this delta B? Well, this area. Okay. Area under this distributed loading is delta B. Why? Well, because that's what the equation says. Delta B is area under the curve of W is of a negative distributed loading. So if you figure out the area under the distributed loading and put the negative sign, that becomes change of shear. Equation says so. Okay? That's delta B. Okay. So this is completely opposite to that. Okay? Beginning with larger negative slope, ended up in smaller negative slope. So one is convex, one is concave shape. But either way, nonlinear change of shear. Okay, that is going to again affect to trickle into moment diagram. Okay, those two doesn't look different, obviously, because here is B1 is bigger slope, here is B2 smaller slope. Anyway, so it doesn't look different. Okay. So, do you have any question?
Yes, I know. I'm a pilot. Pilots are required for intellectual skills.
Do you have any question?
I have a question.
Go ahead.
So for your third example.
Third example. Yes?
Fourth example.
Fourth example, yes? Okay.
Yes, sir.
Yeah.
So let's say like W1 is 15 pounds.
15 pounds, yeah.
The slope
yeah.
of the shear diagram will be 15. Right?
Negative 15.
Negative 15.
That's right. Don't forget about negative sign. Yeah, but negative 15. Good point. So let's just try a very fast example problem. Yeah. Okay. Class example 3. Okay. Am I sharing my desktop? Yes, I do. Double checking. Okay. So let's just take a look at page 12. Class example 3.10.1. So this is your very first shear and moment diagram. I purposely choose the simplest possible example. This is the simply supported beam. You have a pin on A. You have roller at B. So you have the three support reactions. One of them is 0. AX is 0, of course. Okay. So support reactions you have to figure out first, and then you're going to apply P. This is a force applied not in the center, but the location, some arbitrary location, measured from A, the distance A away from it. Okay. So this could be completely 1/2 in the middle, or it could be some other locations. But anyways, what I want to know is I want to extract the generic equation of internal shear and internal moment. And then so I'm going to derive the equation that actually describes the internal shear and moment as a function of x. Does that line up very well with the shear and moment diagram or not? I want to show that. Okay. So very first step, let's just draw a free body diagram of the entire beam. Okay. Okay, so this is a beam AB. I disassemble pin right here. This is actually going to introduce you to unknown support reactions. AY, AX. And also right here, roller B, you are going to have support reaction BY. Okay. And external loading is applied. This is a P, external loading. Location is A, measured from A, pin A. And then rest of the beam's length is B, okay? So as usual, easy one first, you're going to apply summation of the force in x direction set equal to 0. Let's say this is positive x. This is going to give you very simple result. AX must be 0 because this is the only force in x direction. That means no normal force. This is 0. So you're interested in AY and BY, and let's do a summation of the moment. Let's say this is a positive direction moment. Summation of the moment at A, let's just set equal to 0. This P create negative moment around location A. So this is negative force P times moment arm A, right? PA, negative PA. Okay? And this BY support reaction create positive moment BY times moment arm is A plus B. Let's just set equal to 0. This is going to give you support reaction BY. BY is whatever the magnitude P is multiplied by the length A divided by length A plus B. Okay, so this is support reaction BY represented by external loading P and then distance A and B. Okay, first of all. And then summation of the force in Y direction. That's the next step. Let's just set equal to 0. This is going to give you AY is positive, and then BY, which we know it is PA over A plus B. This is BY. And then minus P is equal to 0. So this is going to give you AY, which is, now this is P times B divided by A plus B. So this is support reaction AY and BY represented by magnitude of external loading P and then distance A and B. Okay. So those are the support reactions. Good. That's the first step. So by observation, what kind of shear moment diagram you can expect? Do you think shear changes? Yeah, of course shear changes, but which location you think shear changes?
How did you get AY?
AY is equal to P minus PA over A plus B. So P minus P over A plus B, which is equal to P times, I don't know, I can't do math. It's P times 1 minus A over A plus B, right? Which is P times, what is it? A plus B minus A over A plus B, in which P over B over A plus B. Right? Sort of. Okay. Okay. Yeah. I hope I'm not going to go run out of space, but let me just keep this for a moment. I may erase it later if I'm out of space. But okay, so you have to observe it. In other words, from location A to the point where you apply external loading P, internal shear stays constant because there's no distributed loading. Okay, it doesn't change the internal shear because of that. But you apply the point force here. At that point, you have a jump of shear, right? So let's say, okay. So first of all, for the range of this, let's say I'm going to set coordinate. This is x, okay? So if the x range is from 0 to A, I'm going to introduce a cut. So I'm going to cut. Okay? That actually represents what is the internal shear and moment in the range from here to all the way to there. So I'm going to cut and introduce cut free body diagram. Okay. You already know the support reaction here. This is PB over A plus B. So that's the support reaction here. And then over the cut segment, you're going to introduce internal shear B. Let's say this is a function of x. It may not be constant, so this is a function of x. X range from 0 to A, okay? This is internal, let me just change the color, sorry. So you're going to introduce internal shear, which is, I'm going to follow through the sign convention, okay? So this is internal shear function of x. This is also internal moment, also a function of x, okay? Let's find out those two. Summation of force in y direction. Set equal to 0. This is going to give you PB over A plus B is equal to B. Oh, that's it. So in the range of 0 to A of x, shear is a constant. It's not even a function of x. Oh, it's a constant shear. This is the value. Oh, okay. Now I know it. So what about, let's do sum of the moment. Let's call this point O. Sum of the moment at the point O, let's just set equal to 0. And this is going to be what? This is x, of course. So this support reaction multiplied by this distance x is going to create negative moment. So that is equal to mx. So that is PB over A plus B times X is going to create negative moment, which is equal to mx. Oh, so that is, wait a minute. So that is moment, isn't it? Let's just be careful. So multiply by x, okay? So this is PB A plus B times x is equal to essentially the moment. This is a function of x. This is a function of x. Oh, moment is not a constant. It's a function of x. But you know what kind of function it is. That much I know. Do you follow? So shear is a constant, but moment is not a constant. It's actually a function of x. But I know what function it is. Okay? Right. And let's just introduce another cut here. This is in the range from x equal to A to B. Okay. A to actually A plus B. Sorry about that. So another cut is introduced here. This is the range that x is equal to more than A but less than A plus B. Okay. So what do you mean by that? If the x is equal to from here all the way to here. Okay. So if you introduce this cut, I have this kind of free body diagram. We know this is a support reaction PB over A plus B. Okay. So now this is x. And as usual, you're going to introduce shear as a function of x and also moment also as a function of x. Okay. Now, in this free body diagram, of course, you have to include force P in your picture. Okay. So now what happens? Interesting thing is you have to be very careful about dimensions here. Dimension-wise, this is A. This is x minus A. Okay? I hope we have enough space. Okay. Okay, now let's just do the same thing. I'm going to apply for this free body diagram. I'm going to apply summation of the force. Y direction set equal to 0. And what happens? Well, you have P times B over A plus B minus shear force as a function of xbx minus P. This is external force applied. All of them added together is 0. This is going to conclude shear internal shear developed in the range of x from A to A plus B is negative PA over A plus B. Okay. Well, of course, similar mass, something like this need to be done to get this, but okay, I'm going to skip it. So this is, once again, this is not the function of x at all. This is a constant value, but the different constant value, right? So obviously shear all of a sudden changed across this line. So internal shear in the range from here to here is this value, but from here to here is this value. Shear changes. How much change do you think it is? This much change. Because you're applying force P, you change the shear, of course, yes. The next, okay? So let's just do a summation of the moment, okay? Summation of the moment, once again, I'm going to put 0.0 right here. This is 0.0. So summation of the moment at 0.0, this is positive direction, let's just set equal to 0. This is going to give you, okay, well, this creates negative, this creates positive moment. So negative moment is negative PB over A plus B multiplied by X. That's a negative moment created by support reaction. Then this P creates positive moment. Positive moment P times this distance, X minus A, P times X minus A. And then Mx, of course, it's positive. It's plus Mx. M is a function of X. Is equal to 0. This is going to give you a moment, internal moment developed as a function of X is equal to PA minus PA over A plus B. X. So this is the moment as a function of X. This is also a moment as a function of X. Shear seems to be constant and constant, but the two different values. Okay, so that much I know by introducing virtual cut for two locations. Now let's just draw a diagram. I'm going to kind of zoom out and then show an entire picture here. So let's just construct the diagram here, okay? So I'm going to basically draw a vertical line. Vertical line. Okay. I'm going to set the coordinate. Okay. So first of all, you are going to construct the shear. So I'm going to set the shear diagram. So this is X direction. This is the shear B. Okay. And also, I'm going to construct the coordinate for running out of colors, but I'm going to set up the coordinate also again for moment. This is X. This is the moment. Okay? Okay, so if you look at the shear right here at the very end of the beam, you have a support reaction AY, which is PB over A plus B. So you have a jump up this much value. Jump up. How much value for that? Of course, this is going to be PB over A plus B, right? And shear is going to be constant until you hit this external loading P, right? If you see external loading P, you have a jump of shear. How much jump do you have? P. So you're going to jump down shear this much, P. And now shear becomes constant, constant, constant until the very end of the beam. How much value for that? What's this value? This is negative over PA over A plus B. That's right. Then here is a BY. Suppose reaction shows up. Jump up, go back to 0. This is the shear diagram. Does it make sense? I hope. Okay, so this is how you construct the shear diagram. Okay, so by the way, you don't need those equations. Those equations are there. I try to show what kind of internal shear and moment expressed by equation as a function of x. But in order to construct the shear diagram, you don't need to know that kind of equation. This is what it is. You have a jump, constant, you have a jump, constant, you have a jump. Okay? So what about moment diagram then? Once you construct the shear diagram, moment diagram is based on that. So moment diagram is starting, of course, from 0. Starting from 0. So from here all the way to here, you have a constant shear. Constant shear means constant slope of a moment diagram. Slope is this much. Constant slope, straight line, straight line, straight line, until you hit this point. Right? Slope is PB over A plus B. So what is this value there? That's the area here. Okay? So if you find out the area, this is PB over A plus B times A, isn't it? So this is PB over A plus B multiplied by A is the value here of the moment. That is essentially this area. In other words, delta M is the area under the shear diagram. This is the constant slope. Slope is this value, starting from 0 all the way to the point where you apply P. The value is this.
Is it technically PB over A plus B times X, not A?
Because X equal to A here.
Oh, okay.
That's right. Yeah. Okay. Good question though. Okay, anyways. So the rest. Interestingly, so at this point, you apply force P, so all of a sudden, your shear internally becomes negative. What do you mean by that? You all of a sudden experience negative slope, but the negative constant values throughout. Negative constant slope. So you're going to draw a straight line from here all the way to the end. Okay, so this is a slope. Slope is equal to basically PB over A plus B. This is slope is negative PA over A plus B. Constant slope, because it's a constant shear. Starting from this value, go back all the way to 0. This is moment diagram. Go ahead.
These are only negative and positive based on like convention, right? It doesn't actually.
Yeah, that's right. So we set the convention first. Yeah.
So if you were to go, say, from the other direction, it would be inverted.
We don't want to think about it. Everybody need to follow convention. Otherwise, we don't we don't want to confuse. So if you want to express this as a mathematical function, obviously you can say this. One thing if I want to add, if you want to this as a mathematical function, this is moment as a function of x is equal to pb over a plus b x. This is a mathematical function of moment in which you found it here. You found it here, pb over a plus bx. That's the moment as a function of x. That's what this curve is. This is a linear function with a slope of this, y equal to ax equation, right? You understand? And mathematically, if you represent this line, this is moment as a function of x. This is equal to pa minus pa over a plus bx. Right? This is y equal to ax linear function with a slope of this negative pa over a plus b, isn't it? And then if you extend this all the way to go across y axis, it is going to be pa. So this is the starting point pa, linearly decreasing function with a slope of this, y equal to negative ax. Make sense? So this is a linear function. So a moment is represented by two linear functions for this case. Lucky for you, because this is a simply supported beam. How's that? Beam can be super confusing. You can apply 20 different forces in every which direction. You can apply distributed loading. You can apply moment. You can you can make the beam super complicated. But this is something controlled by, everything is controlled by a governing equation. You have to understand it to begin with. So this is a simple illustration of what's going on inside of a beam. Okay, so the problem you're going to solve from now on is just to add more complexity, but everything is controlled by a very simple fact that two governing equations control everything. Okay, this is just a demo. Any question? I hope this makes sense. If you basically understood the basic concept, everything else is just application. Okay, do not do opposite things. People just do opposite things. They don't care about knowing what is fundamental concept, but they try to, hey, it's just to memorize and it's just survive and exam and stuff. That's inherently anti-engineering. Okay, so let's just understand that most important thing is this class is engineering class. I want you to develop your engineering mindset. Okay. And then your life is going to be progressively easier and easier as you become senior student. Anyways, so this is a homework assignment. This is actually very simple, isn't it? It looks super confusing, but it's not. This is a simple beam. You have 1 and 2 and 3 support reactions only in vertical direction. It's essentially about the same problem you did today, right? 3 forces involved. This is about the same thing. Okay. Well, this is actually much easier because this is right in the center. So you can almost draw a diagram. Oh, wait a minute, that looks like this. Well, but let's just erase it, okay? You can almost say that, but you're going to supposed to be doing that. By looking at your handout, trying to construct this, okay? All right, this is another example here. Oh. So this is, suppose it's very similar to what we looked at. Suppose instead of a point force, if you have a point moment in this direction, what happens? And I'm not sure if I can finish this problem today, but let's just get started and let's just continue, okay? If we cannot finish. Okay. So this is again, we're going to draw free body diagram of the entire beam to begin with. Then find out support reactions. That's the first step, obviously. So you have AY and AX. And before you even move on to the next page, you kind of know this is 0. So, okay, so this is 0 probably, and it is 0. And this is BY. And then you have externally applied point moment right in the center, which is M0. And let's just double check if this is a positive or negative application. We're going to go back to the handout. M0, this is counterclockwise is going down. Okay, jump down and counterclockwise. So this program is a clockwise, so jump up, looks like. So you are going to expect moment jumping up. Okay, right here. Okay. Next is obviously summation of moment at A set equal to 0. We already did summation of the force in x equal to 0. This is going to be 0. Summation of the force in x direction set equal to 0 is going to give you this conclusion. Ax is 0. So next step is summation of the moment at point A set equal to 0. This is going to be by times L minus M0 is equal to 0. So this is by is equal to M0 over L. So this is support reaction by represented by externally applied moment and the length L. Summation of the force in y direction set equal to 0. This is going to be AY plus M0 over L is equal to 0. This is going to give you AY. Support reaction is negative M0 over L. This is a support reaction AY represented by external moment M0 and the length of the beam L. Okay, so that's the first step. Then again, interestingly, since you have only point moment applied right in the center of the beam, you are going to expect probably uniform shear throughout the beam because the external moment does not change anything of the shear. So you can almost draw straight out the shear, but let's just find out. Let's just introduce cut here. So for the range of x, once again, this is x. This is x, okay? I'm going to set the coordinate. So for the range of x, 0 to half L. So starting from here all the way to the location of external moment, you're going to introduce a cut, okay? Then pick up that cut segment as a free body diagram. And of course, you know AY is negative. Well, it's negative, so that's just a flip-flop. Damn it. Sorry about that. Okay. So we got negative value. That means, hey, direction is this way. Okay. So flip-flop the support reaction, and then let's remove negative sign. M0 over L. This is the support reaction at point A because it's negative. And so this is the x, okay? All right, so let's say this is point O. You're going to introduce internal shear, which is shear B, as a function of x. And also internal moment, bending moment M, also as a function of x. Okay. So I'm going to apply summation of the force. Let's say set in y direction let's say, summation of the force in y direction set equal to 0. This is going to be the negative m0 over L minus shear as a function of x is equal to 0. This is going to give you shear as a function of x, in which negative m0 over L. Whoa, wait a minute, this is not even function of x. That means it's constant. The shear is a constant, which is this value. Okay. And then also suppose, oops, 5 more minutes. Let's just do this once. Okay. Sum of the moment at point O set equal to 0. This is going to be internal moment as a function of x plus m0 over L times x gives you moment is equal to 0. This is going to give you moment as a function of x, in which minus m0 over L times x. Oh, this is a function of x. That's right. So now we know both internal shear and internal moment. One is a constant, the other one is a function of x. And then let's just stop here. So as you come back on Thursday, we are going to introduce another cut and find out, okay, so in the range from half L to L, what is the internal shear and internal moment as a function of x? Then after that, try to draw shear and moment diagram, okay? So let's just stop here, make sure I'm going to save it, whatever it is. Okay, and let's just do a quiz today. Do you have any question here? Ready to go for quiz? Okay, I'm going to stop recording.